Welcome back to ECE 220. Lab has started. We had a little bit of a confusion I hear yesterday. There's one overlap of two sections. Section E and Section I share Tuesdays, but we're skipping weeks. If you're in Section E, you should have attended lab yesterday. Section I will attend lab next Tuesday. Section F is today. So make sure you look on your, U-Access somewhere, find your section. It's 006, a letter, and that letter is E, F, G, H, and I. And I've tried to give you where you belong relative to a calendar or relative to the dates on the schedule for the labs, and that should be available on the website if you can't find it for your particular section on U-Access. But if you are going to lab this week, which F, G, and H will on Wednesday, Thursday, and Friday that remain, please make sure you're bringing something to take notes with, and you have your CAT card, and you have closed-toed shoes. Those are the requirements for the orientation lab for this week and next. Pspice, you need to make sure that you have access to Pspice either on your own machine or in room ECE 232. That's due in class, that homework assignment on Pspice on Friday. Homework 3 is due next Tuesday. The following Tuesday is homework 4, which won't be a part of exam 1, but exam 1 is then the subsequent Thursday on the 26th of September. Today what I want to do is finish up chapter 3, and then we'll move into chapter 4. Chapter 4 is starting tomorrow, Thursday. That will not be a part of exam 1, but that doesn't mean you shouldn't stop attending, or you should stop attending class. I don't want to say stop. You want to continue attending class, and homework 4 will be part of, or when it gets built, will be covering chapter 4 material. And that will be additional ways to solve circuits. Resistive circuits. Today we're going to go through some examples. We'll look at a practical example for loading. Then we will look at an example that has a network of resistors interconnected that's hinting at a bridge. And so now we might say, is it a bridge? Is it a plane? No, we're talking with bridges in this class, so now we need to find out, is it a bridge? And if it is, what does that allow us to do relative to analysis? We'll look at an example that involves a delta Y conversion, and then we'll go into an imaginary space, or a component that's imaginary. We'll start talking about complex numbers. How many have seen complex numbers already? Quite a few. It's Appendix B. If we don't get there, you can start refreshing or learning about complex numbers by looking at Appendix B in the textbook. Let's start with a trip down memory lane. And this is a practical example of the loading effect. I'm sure most of you were disappointed when you realized Dr. Marcelin wasn't teaching this class. He's on sabbatical this semester, but before Dr. Marcelin stepped in and was teaching 220 regularly, Dr. Strickland was teaching this class. He came up with the following example. So, this is a trip down memory lane relative to instructors. This is a few instructors prior, but here is a scenario. And you know, if you've ever been to my office, that I couldn't have something like this in my office, a hot plate or a lamp. I might start a fire. My office is a mess. So Here's another office. Here's Dr. Strickland's office. And if you're interested, I guess, to see my office, you can see that during office hours on Mondays and Wednesdays from 2 to 3 and Fridays from 11 to noon, traditionally. Here's Dr. Strickland's office. He has a power strip and the potential to plug in a lamp and a hot plate or something to heat up water. Dr. Strickland was from England, so he liked his tea. So I'm sure he had tea in that cup or on his hot plate. And there's a switch on the hot plate. I apologize for the artistic or the lack of artistic ability, but I hope you can use your imagination. You can now envision a power strip with a lamp and a hot plate, and we can turn that switch on the hot plate on and off to change the load to the system. And this system we're dealing with is coming out, the power that we're supplying is actually coming out of a wall socket, and that is not constant. If you look at the voltage waveform coming out of a wall socket, it's oscillating. It has a frequency of 60 hertz. But if we're dealing with resistive type loads and other problems, a lot of times we like to convert that oscillating waveform into something that looks effectively like a constant waveform, and that we do by finding its RMS value. Coming out of the wall is something that's banging between 170 and minus 170 at 60 hertz or 60 cycles, 60 times a second. Well, we take the root mean square of that, which really, you do it sort of in the reverse order. You square that waveform, then you look at the average, and then you take the square root of that, and you end up with 120 volts for this sinusoidal waveform of 60 hertz that has a peak amplitude of plus and minus 170 roughly. Now, we'll just view that 120 like we've been doing in this class so far as if it's a constant signal. So now we have 120 volts available to us, and we want to now drive or turn on a lamp and a hot plate. Here's the circuit model description of that. We have the power strip and cable. That actually does present some resistance. It's wires, but in practice, those wires do have some resistance associated with those. Dr. Strickland actually measured that, and it ended up being 0.7 ohms. He also measured the resistance of the lamp to be 23 ohms, and of the hot plate, or actually he had a kettle, so I just couldn't draw a kettle, so I settled on a cup with a hot plate. So I'm kind of changing history here, but I think we'll still have the same learning opportunity. I'm calling it a hot plate of resistance 10 ohms. And we can switch whether or not we have that hot plate on or not. With the switch open, now I want to find the voltage V. Can you find V with the switch open? And this, I said we were going down memory lane. You don't even have to go back in time to Dr. Strickland to analyze this. We've done this semester. You now can find an equation for V with the switch open. How much current is flowing in that rightmost branch or in the hot plate with the switch open? 0. We can neglect that with the switch open. And now what do we have? We have 2 resistors in series with basically an effective DC source. V using a voltage divider, which I'm hoping you already wrote down, is going to be 23 over 23 plus 0.7 times 120. Here we have the lamp in series with the power strip. And that allowed us then to write down this voltage divider, and if we multiplied all of that out, we would end up with 116.5 volts, and we're using now RMS units, not DC. These are effective voltages, or RMS. So that's 116.5 volts RMS. What happens now if we have the switch closed? Now what happens? Now we have some current feeding that hot plate. Can you still solve the problem based on the strategies or techniques that we've learned in this class? Can you find the voltage V with the switch closed? So now we have really the lamp and the hot plate in parallel, and we can combine those resistances as resistors in parallel, and then we have an R2 new, or an R2 hat. We've been sending these R2s to a party when we have them in parallel. We now have an R2 equivalent, but now we can use the voltage divider again with a modified R2. With the switch closed, we now have 10 in parallel with 23. And you know how to compute that. The product of those two divided by their sum, you end up with 6.97 ohms. Whoa. Okay, well, I couldn't remember what all I'd included. Now we're ready to go. We can find V. What's the formula for V? Is that what I heard? So this is now V with our new R2 hat, or our R2 equivalent. That's what this is. This is our R2 hat. And this, we said, is now R2 hat over R of the cable plus R2 hat times our source voltage. And if you multiply all of this out, you end up with 109 volts RMS. And what's happened? What's happened when we switched the hot plate to the voltage now seen by the lamp and the hot plate? They're the two cases. The voltage went down, didn't it? It decreased when we switched the hot plate on. What would you expect to maybe feel or see in that scenario? The light dims, doesn't it? Because now the power that light experiences, we can write it as V squared over R. And V squared has changed in the two scenarios. The lamp now, without the hot pot or the plate on, has 116 volts across it. We square that and divide by R, and what was it, 23? So we could find the power in the lamp before or with the switch open, and we could find the power of the lamp with the switch closed. And obviously the lamp is seeing less power. With the switch closed, the lamp dims. So that's a practical application of this loading effect. The voltage at, well, let me just say voltage decreases across the loads. And we could think of that another way, is that hot plate now is pulling current off of the circuit, but we could also say if V is now less, what's the voltage drop across that power strip and cable when the switch is open versus when it's closed? We have a larger voltage drop across that power strip or wire when the switch is closed. So if there's a larger voltage drop, what's the current like in that resistor? Ohm's law. Ohm's law. V over R, right? So now if we have a bigger numerator, the current has increased. We have more power being consumed by the power strip when we attached another load to that device. And I said, what will we sense by seeing or feeling? Now if we grabbed the cable supplying that, we might see an increase in temperature in the wire because there's more current flowing. There's more I squared R losses in that cable. So let's just say that with the switch open, let's not say, let's now write down with the switch open, the power, let's say in the lamp, is this V squared over R, and the V squared was 116. I didn't write it down, but this is now 590 watts. With the switch closed, the power formula is still the same. It's just that our V has changed, and now we have 516 watts on that lamp. So that's the impact of loading, practical impact. You add an additional resistor in parallel, you're loading the original network, and you can't just use the standard voltage divider formula for that. So now you can go home and play with all of these different scenarios. You can create your own electric circuits, etc. Let's now look at another example. And now I want to find V sub 0 in this circuit. I'm supplying this network of resistors with a current source of 10 milliamps, and my resistors have Ks after them. It's 1K, 3K, 4.7K, 3.3K, etc. And I want to find the voltage dropped across V sub 0. Is there any voltage dropped across V sub 0? What's happening at V sub 0? And that 4.7K and 3.3K resistor are not connected. There's a gap between those two resistors. Is there even any voltage dropped across V sub 0? What's the current flowing through 4.7K? 0. What's the current flowing through 3.3K? It's 0 as well. There's no current flowing in that middle branch. So what is V0? Is it 0? Well, this is a good question, isn't it? So if we want V sub 0, do you see that that's equivalent to the voltage dropped across those two terminals? V sub 0 is the same here in blue as it is in red. That's the same potential. Because if I connected something to that the right side of that 4.7, then I'm going to be really effectively measuring the voltage on its left side, because there's no voltage dropped across that resistor. The same with 3.3. And you could write a KVL around that and see that minus V0 plus the 4.7K times 0 plus V sub 0 plus 3.3 times 0 is equal to 0, and the V0s are equal. Yes?
If you actually use a real voltmeter, not an ideal voltmeter, wouldn't you create a series connection across?
So now the question was, if you use a voltmeter across those 2 points, don't you create a path for current? Yes, you do, but your voltmeter ideally looks like a very high impedance relative to these resistors. So you're not going to draw too much current, and you won't change the voltage measured too much, but in the lab you will be calculating the percent error between the real or the measured and the ideal. But here, V sub 0 is the same, red or blue. If V sub 0 is blue, if that's the way we want to look at it, what would be a very quick answer to this if I had designed the problem properly? Or what would be a quick way to find V sub 0? And now I'm hoping you see some structural piece to that network. What does that kind of look like? If it was connected, if those 4.7s and 3.3s were connected, what would we call that network? It would be a bridge, wouldn't it? That would be that bridge interconnection. And what do we know about bridges? If they're balanced, then what do we know about V sub 0? If this bridge circuit was balanced, there would be no voltage across those two nodes. There would be no current flowing through that. And that's the scenario we have here. There's no current flowing through that. So if it was balanced, we could immediately say V sub 0 is 0 if it's balanced. So so our thought process is this really a balanced interconnection of resistors? If it is, this will be a quick problem. So here's our thinking. There's no current. First, I hope we learn that there's no current flowing in 4.7K or 3.3K. Now we want to know, well, is our circuit balanced? If it is, then we know what V0 is. If it's not balanced, we need to calculate it because, well, there's a lot of different ways we could calculate it, but if we said something like this is now V1 and this is V sub 2, we could now write a KVL keeping track of V sub 0. If V1 is something and V2 is something, then we know we can calculate V sub 0. If it's balanced, we know V1 and V2 are the same. Pardon? We can do KVL if it's open or closed. We can write KVL with an air gap. So our KVL in the lower part would be minus V1 plus V sub 0 plus V sub 2 equals 0. That's the KVL. But before we even get there, we could say, wow, if this connection of resistors, the 1, 3, 6, and 2, if that's a balanced set, we know now that V1 is the same as V2, and V sub 0 would be 0. Is the network balanced? And do you remember how we determined if our network was balanced? Here's sort of this R5 that we were thinking about, and we needed for this product to be the same as that product, diagonally across the bridge. To check if this system or network is balanced, we now can say, oh, is 1 times 2, I'm going to leave off the K's, but these are in kiloohms, but those we can cancel, is equal to 3 times 6. And that we can quickly see. Is our network balanced? 2 is definitely not 18, is it? So we can't immediately conclude that V sub 0 is 0. Maybe I should say it another way. V sub 0 would equal 0 if the network was balanced. Bummer. Now we have to do some more work. We were hoping that the product of those paired resistors would be equal, and then we could say, it's balanced, V sub 0 is equal to 0. Move to the next question. We can't do that now, can we? Can you see a strategy, though, for analyzing this circuit now? Boy, it's a lot of highlight, a lot of lines going. We can put on the right glasses and erase all of that. What's another way to look at this? Now I would virtually erase what I have in yellow highlight. That makes no difference to you now. Right? Those two disconnected resistors you can just forget. Just throw them away and say, okay, now I have, what do we have? Well, I have a 1 and a 3K in series. And I have a 6 and a 2 in series, and those combinations are actually in parallel. I have a current divider. That's our thought process. So now what we see is now we say, therefore, the 1K and the 3K are in series. The 6K and 2K are in series. And, in fact, if we call that I1 and this I2, do you see that I1 is going through the 1-3 series combination and I2 is going through the 6-2 combination? So this now passes I1 and this passes I sub 2. And 4k, that's why I didn't write k's around all those. I can't write a k to save my life. So now 4k is in parallel with 8k. That's what we get when we sum 1 and 3 and 6 and 2. And these are in the vertical branches. And those vertical branches are in parallel. Now that we see that we have two parallel branches with a current source, we have the standard current divider scenario. What's I1? What's the formula for I1? Our current divider formula says we take the opposite branch, which is 8, and divide by the sum of the two branches, and multiply by the source, which is 10 milliamps. Here we now have I1 is now 8 over 4 plus 8 times 10. And these are all K's. I wish they would have done L's instead of K's, but I have to do K's because K is meaning 10 times 10 to the 3. So the milli and the K's cancel, and now we have 8 over 12, or 2/3 of 10. Is that right? So this is now 20 over 3 milliamp. I should have said the K's cancel. I still remain with the milliamp. What's I sub 2? You could do another current divider formula, or you could write KCL. You know I sub 2 is what's left over when you take I1 away from 10. With a KCL at that node. N equals out. 10 equals I1 plus I2. I2 is equal to 10 minus I1. I sub 2 is now 10 over 3 milliamps. Question? The what? Yes, I messed up. So the question was, didn't you say the K's and the millis cancel? No, I did say that. I shouldn't have. The K's in the current divider cancel, and so now we just have a fraction of the milli. Sorry, so I was just looking at the numerator multiplying the 10, and I forgot about the denominator. So we can't cancel the K. So that would have been, I would have gotten 20 over 3 amps out of 10 milliamps. That's not going to happen, right, in our current divider. So I misspoke. Hopefully you can erase that. Rewind. Erase that period where I said those cancel. They don't. The K's cancel, so I shouldn't have even written the K's in there. I missed my chance. I don't like to write K's. I shouldn't have written them in the first place because they cancel. What were we doing? Where are we? What day is it? We're playing with a bridge. That's right. We've got a bridge. We wanted to find V sub 0. Do we have enough information to do that now? Can we find enough, can we calculate enough to find V sub 0? And now we can. We can do this KVL. We have minus V1 plus V0 plus V sub 2 equaling 0. Or V sub 0 is now V1 minus V sub 2. And V sub 0 is, what's V1? Now the K's and the M's cancel because we are doing Ohm's law. So now we have, what's V1? With the variables that are on the screen. Ohm's law. It's 3K times I1, which is in milliamps. That's V1. So this is now 3K times I1, which is 20 over 3. So this is now 3 times 20 over 3. And now the M and the K cancel, so I'm not going to write the K. I'm not going to write the M either. That's V1 minus, what's V2? That's 2 times I sub 2 in K and milli. 2K and I sub 2 was 10 over 3. So we now have 20 minus 20 over 3. Or (40/3 volts). So we have a significant voltage drop across that air gap in our bridge. 40 divided by 3. A little over 13 volts that would appear across that air gap in our bridge circuit. Maybe before we move on, what if I wanted to balance that bridge? What if I wanted to make V sub 0 equal to 0? How could I do that? And that's what you're doing with a Wheatstone bridge configuration. You're adjusting something. You could now adjust that 3, which I think we called R sub 3 in our bridge. You could adjust that, or you could adjust R4. You could adjust any of these until you did have that paired product equaling 0. In a Wheatstone bridge, you might put in an unknown 2, so you don't know what that is, and you're adjusting R3 to get 0 current through that bridge. And then you know how to find R4. It's just the product and division of R1, R2, and R3 from that equality. Question? So what would the practical application of a bridge be? I just tried to explain it. Obviously it wasn't very good. One way would be to try to figure out what the unknown resistor is here. Suppose this you didn't know. Maybe this is now R sub X. And you can adjust this one. This R sub 3 is adjustable. Somebody gives you a box and they say find out what the resistance is. Now you know what R1 and R2 are up above. You know what R3 is because you can adjust it. Now you know, because of the relationship of R1 R sub X is equal to R sub 2 R sub 3, you now can say R sub X is R2 over R1 R sub 3, and you're adjusting this. Now you see what you adjusted it to. You know R2 and you know R1. You can now solve for R sub X. So you adjust sub 3 until you have zero movement on that dial in the bridge. You're trying to get zero current flowing or 0 volts dropped across that bridge. You adjust R sub 3 to make that happen. R sub 3 now is this decade resistor box, and you can read off exactly what that is, and now you can get a very accurate measurement of R sub x. That's one application of this bridge network. But you can see that you could use this in many different kinds, maybe, of sensing environments. Question? So now if there's no current going through 4.7 and 3.3, why is there a voltage drop across that gap, right? So now, if there's no drop across the 4.7, that effectively is like a wire now. The 3.3 looks like a wire as well. If those are wires, now do you see that you can connect, instead of the red V0, it's now the blue V0. Correct. So there's no voltage drop. You're not losing anything. So that's why the red V0 is the same as the blue V0. There's no voltage dropped across 4.7 or 3.3. So look at that and make sure it makes sense to you. Now, just say there's a I7 going through 3.3 and an I8 going through 4.7. And those are both 0, those currents. So you've got, from Ohm's law, 0 volts dropped across those two locations, or those two resistors. That means now that the red V sub 0, we can expand, since there's no voltage drop, and it's effectively the blue V0. And now with KVL, we found the difference between this point, which we could have labeled A, and this point B. We could say, well, what's the difference in voltage between point A and point B, node A and node B? We can put our voltmeter across those, and we could now measure whatever we just calculated, which was what, 40 divided by 3 volts. It takes a little getting used to. It's kind of weird. How do I have, because initially, you were arguing there's no voltage, V sub 0, since there's no voltage on the 4.7, there's no voltage on the 3.3, and I've got an air gap there. It's got to be 0. No, because it's effectively between A and B. That you have to kind of get clear in your own head, and it takes a while. So now, let's look at this one. Suppose we now want to find 3 variables, I1, I2, and V. Oh, and I need to give you the last. I just assume that everyone here is just so dedicated that they probably print this out the night before. Obviously, it's kind of late by the time I get these available. And you just work through all of this, and then you go, I'm just going to relax during class. That's why I leave one of those unlabeled. So you can't work ahead too far. But you could always plug in something, or you could try to guess. How many of you actually worked this last night? Oh, great show of hands. That's okay. I didn't expect you to, but that's why I leave that off, just in case somebody is very dedicated and they say, let's work this ahead of time. Now, how do we approach this problem? Using material from chapters 1, 2, and 3. We want to find I1, I sub 2, and V. And a lot of times it's actually helpful to be thinking as you're drawing that circuit, thinking through what is actually happening. What do I have available? What can I find? And maybe you're I never know how much to lead you down the wrong path in your thought process. I don't know if that's going to be effective. But how many of you, in looking at saying, oh, I need I1, if I just knew what the current was flowing through that 30, well, there's two 30s, the leftmost 30 ohm, could I find I1? If I had the current coming out of the 500 volt source, is really what I'm asking. If I had that current coming out of that, could I find I sub 1 immediately? Could I apply the current divider to find I sub 1 if I knew what was coming in or coming out of the 500 volt source? No. So you can't do that. So you kind of have to play this forwards and backwards and coax these different variables out of the process. Wow, how am I going to can I find V? Is V 0? Did you do the bridge? Is it balanced? So if the bridge was balanced, V would be 0, wouldn't it? But is that bridge balanced? No, probably not. I haven't even looked. 10 times 182 equal to 30 times 44. That doesn't appear to be the same, does it? So the bridge is not balanced. We can't do that, but on an exam you might want to check. Hint, hint. I don't know. I wish the exam was built and ready to go, but it's not. So I don't know what'll be on the exam, but if it was balanced bridge, are we okay that V would be 0? It's not. So now we don't know what that is. Is that a voltage divider some way? That's a mess, isn't it? What about I2? Anything we can do there? We're going to have to kind of go piecemeal in this, aren't we? Oh, that clock. That clock. Can I just Wheatstone bridge it, make it go away, drive it to 0? I just about fell over walking up. I have to move around so that I can think. Did you know that? So now if you get up on the exam and you start doing jumping jacks, my workshop last Friday, they asked the question, does physical activity help with your mental cognition? I said, yes, it does. It was right. That was the right answer. Anyway, if you stand up, at the table I was sitting at, I said, yeah, I let my students do calisthenics in class. She goes, you do? I just let her think we did. So we all can just do some jumping jacks occasionally. Where was I? I was worried about the time, and what am I doing? I'm blowing it. So how do we apply this or solve this in a few minutes? What's the thought process? And you can do this now at home. We're probably going to have to do a delta, well, I gave it away, didn't I? A delta Y conversion. Why don't we convert that leftmost piece of the bridge network into a Y? It's now in a delta. Do you see that you could call, however you wanted to label this, you could say, stop. This we could maybe say is A, this is B, and that's C, and you could redraw it. And now you want to find R1, which is here, R2, which is there, and R sub 3, which is there. And then we could start to maybe simplify the circuit. Now we get rid of that 60 ohms. Now this 60 here is going to go away, and we remove that bridge from our network, And now we can start simplifying that resistor combination. So we would erase or redraw. I would probably just redraw that ABC into the Y configuration. Yes, question?
When you convert it into the Y and then you solve for the current, do you have to convert it back to the delta to find the original I1?
Did everyone hear that? So the question was, now that you've converted it into the Y, can you use that to solve for some of these unknown variables? No, sometimes you have to convert back. So you may have to go backwards. So this is kind of the 1 step forward, 2 step back, but actually on the exam, go 2 steps forward and 1 step back will be better for your grade. Okay? So yes, we may have to go forward, go back, go forward and back to iteratively find I1, I2, and V. See if you can do that. If you have questions, come to office hours. We're going to start Chapter 4 tomorrow. See you tomorrow.